Hi guys. So today we're going to start by reviewing some things that you learned about quadratics back in Algebra 1. Then what we're going to do is we're going to look at how to graph these as parabolas, which will include two additional parts that you haven't looked at in Algebra 1. So to start, we're just going to review our transformations. So from the beginning of the year, if you remember, if it was inside the parentheses, those were our horizontal changes. So this graph has gone right 1. Outside the parentheses is vertical, so this graph has gone up 3. Been reflected over the x-axis and also has a vertical compression. The vertex of this graph, since it's in vertex form, would be at 1, 3. Axis of symmetry would be at x equals 1. And then let's go ahead and graph this. So I'm going to go ahead and start by plotting the vertex. We know that this is going to open down because it has a negative a value. Where you get the rest of your points for this graph is dependent really on the method that you've learned back in Algebra 1. You may have learned to do a table of values and plug in points, and that will work. So if you want, you can plug in different x values, like if I plug in 2, so 2 minus 1 squared times negative 1/2 plus 3, and that would be at 2.5. I could plug in 3. 3 minus 1 squared is 2, 2 squared is 4, so negative 2 plus 3 is 1, and those would be points on my graph. The other thing that I can do instead is I can consider how this point's been transformed from the parent function. Now, it is important in whichever method you use to at least understand the shape of the parent function and the general transformations so that we get an idea of what this graph will look like. We know this graph is going to have this general shape to it. We're just trying to get some more specific points. So what I can do is, like I said, consider the parent function. So we know the parent function has a vertex at 0, 0. Well, if I shift or stretch or compress or reflect, if I reflect or stretch that point, it's not going to change it. It's still going to be at 0, 0. The only thing that's going to move the vertex is shifting it, which we already did. Now think about every point in relation to that vertex when you graph it. Well, typically your quadratic parent function from the vertex had a point at 1, 1, 2, 4, and 3, 9. The first point went right 1 and up 1 from the vertex. The next point went over 2 and up 4 from the vertex. Next point went over 3 and up 9 again from the vertex. Well, if we consider that on this graph has been reflected and vertically compressed. So instead of going up 1, I would go down 1/2. Instead of going up 4, I would multiply negative 1/2 and go down 2 and go down negative 4.5. So from that point, if I go over 0 and down 1/2, I get another point. Again, from the vertex, over 2, down 2. And that gives me this point. Then my next one, from the vertex, over 3 and down 4.5. Then, since we know there's an axis of symmetry, we can have those same points that are just reflected over that axis of symmetry. And again, those are the same points that I would have gotten just from plugging in. Okay, I also got 3, 1, and 2, 2.5. All right, so what we can also do on this graph, let's find the domain. So this is going to be from negative infinity to infinity. Range is negative infinity to 3. This graph is increasing from negative infinity to 1 and decreasing from 1 to infinity. All right, on my next one, if I want to look at transformations, I'm going to need to put this in vertex form. But before I put it in vertex form, it is still possible to find the vertex here. I could use that equation that I learned about back in Algebra 1, where the axis of symmetry is x equals negative b over 2a. That's also the x-coordinate of the vertex. But since we need to find our transformations, let's go ahead and complete the square. 2 gets factored out. I leave a blank. Then if I'm adding something, I'm also going to subtract something. So the plus 3 is out here. I'm going to subtract something. To get the number in the blank, I'm going to take negative 2, divide it by 2, and square it. So 2 times 1 would then go here. So I have x minus 1 squared plus 1. And now my equation's in vertex form. So now I can list my transformations. Right 1, up 1, and a vertical stretch by 2. The vertex is at 1, 1. So we'll go ahead and plot that. And then my axis of symmetry is going to be at x equals 1. So now again, we know this is going to be a parabola. We know it's going to open up. We know the parent function typically goes through 1, 1, 2, 4, and 3, 9. But because it's been stretched vertically, instead of going from the vertex over 1 up 1, we'll go over 1 up 2, over 2 up 8, and over 3 up 18. Again, this is in relation to the vertex. Okay, in relation to the vertex, over 1 up 2, over 2 up 8. And then just make those mirror image points on the other side of the axis of symmetry, and you have your parabola. The other thing that the standard form equation tells you that you can get besides the negative b over 2a, that c value, that's your y-intercept. And if you notice, we also plotted 0, 3 as our y-intercept. All right, so domain is negative infinity to infinity. Range is from 1 to infinity. Increasing from 1 to infinity. Decreasing from negative infinity to 1. All right, so what we're going to do now is start to look at these graphs based off the definition of a parabola. So a parabola is this actual set of all points that are equidistant from a line and a point. That line is called the directrix. That point is called the focus. So P, and I really should say the absolute value of P, is the distance from the vertex to the focus, or the distance from the vertex to the directrix. So this distance right here would be the value of P, as well as this distance right here. That value would also be P. Same thing if the parabola is going the other way. All right, so this one, that distance between those two is P. That distance right there is also P. One thing you'll notice is that the focus is always inside the parabola, the directrix is on the outside. And there's one more component here that we didn't look at on Friday. So the latus rectum is something that helps us find the other points on our parabola. So that blue line I just drew is the latus rectum. The total length of that is 4p. But really what we'll practically use it more to actually graph, just that first half right there is 2p. So then this other half here is 2p because the whole distance is 4p. What that's going to do is that's going to give us our other 2 points on our parabola. All right, so let's just look at some features of these parabolas. So here is standard form in terms of a conic. There's actually 2 forms that you'll see. We're typically going to use the ones in the first row in this class more often just because they look pretty similar to vertex form. Depending on the book you look at or what you see next year, you may see that other form instead. It's the same equation, it's just been rearranged. All right. So on both of these equations, the vertex is hk. And then, like we said, the distance from the vertex to the directrix is the absolute value of p. All right, so just keep in mind, on the horizontal one, the vertex is hk, but notice that the h is here and the k is there. That gets flipped quite a bit. All right, if the p-value is positive, we're going to do all the stuff first for the vertical. If p is a positive number greater than 0, it's going to open up. If it's negative, it's going to open down. The axis of symmetry is x equals h, just like it has been. And now let's talk about the focus and the directrix. So the focus is always inside the parabola. It's a distance of p away from the vertex. Well, if that's the location, then the x-coordinate is going to be the same as the vertex. But to get the y value of the focus, I would take the y value of the vertex, I need to add the distance of p. The directrix is going to be outside of it, so it's a horizontal line, so it's y equals. And then I'm going to write it, that value, again, I'm subtracting the value of p from the y-coordinate. So k minus p. All right, so now let's look at horizontal. Okay, if p is positive, it's going to open to the right. If it's negative, it's going to open left. The axis of symmetry this time, since we're opening this way, the axis of symmetry is going to be a horizontal line. So it would be y equals k. And then this time the focus, if here's my vertex and there's my focus, the x-coordinate is actually different. So since I'm moving in the distance of p, h plus p would be my x-coordinate, k would be the same. The directrix would be outside, so I would still subtract. It's a vertical line, so it'd be x equals h minus p. And then again, the lattice rectum, the length is the absolute value of 4p. That's going to be parallel to the directrix, and it goes through the focus. So basically, it's going to tell us those 2 points on the parabola. All right, so now let's look at some actual graph examples. So on this first one, it says to sketch a parabola, and it gives us the focus and the directrix. So we're going to start by plotting it. So -2, 0, y equals 4. So since my directrix is above, my graph is going to have to open away from the directrix and towards the focus. We also know that the vertex is going to be halfway between those. So my vertex has to be here. So I have a vertex of -2, 2. I can now see that p-value, since it's opening down, is going to be negative, and then that distance is 2. From the p-value, I can go ahead and actually write the equation. So this would be, we're using the equation 1 over 4a, x minus h squared plus k. So y equals -1/8 x plus 2 squared plus 2. So that's my equation. Then the last thing I need to sketch the graph is to get those 2 points that are on the ends of the lattice rectum. So the lattice rectum is going to be an absolute value of 4 times -2, which is 8. So remember, the entire distance of this is going to be 8. So to get each point from the focus, I'm going to move 4. And that gives me those 2 points. So then from there, I can sketch my parabola. All right, go ahead, pause the video and try the next one. All right, so on the next one, focus is at 2, 0. Directrix is at x equals -2. That tells us this parabola is going to open right. Vertex is halfway in between. Vertex is at 0, 0. All right, then from here, let's go ahead and find the p-value. It's positive because it's opening right, so it's 2. That means my equation, 1 over 4p, and then it's just x squared. Then from here, I can find those other 2 points that I need. So the lattice rectum has a distance of 4 times p, which is 8. So I'm going to move 4 away. And I get those endpoints. And there's my parabola. All right, so same thing, except now instead of being given the focus and the directrix, we're given the equation. That means it tells us the vertex and the p-value. So this one, because y is squared and p is positive, is going to open right. Again, be careful with the vertex on these. -1 is the x-coordinate. -2 is the y-coordinate. So we can go ahead and plot that. P-value, if 1 over 4p is equal to 1 over 8, then p has to equal 2. So since we're opening right, then I'm going to move 2 to the right to get my focus, 2 to the left to get my directrix. So then once I've graphed them, I can go ahead and write them. Axis of symmetry, since it's opening horizontally, will be y equals. Focus is going to be at 1, -2. Directrix is a vertical line, so x equals -3. Lattice rectum, 4p, which is 8. So the total distance is 8. So from the focus, I'm moving 2 and 2. And that's my graph. All right, next one. You'll probably know this one without graphing the other parts, but I want to go ahead and do find the focus and everything else on this one. So we know here the p-value, well, we know it's going to open up because that's positive. We know the vertex is going to be at 0, 1. We know the axis of symmetry is going to be at x equals 0. So now let's find our p-value. 1 over 4p is equal to 1. That means that 4p equals 1, so p is equal to 1/4. So in order to see this a little bit better, I'm actually going to change these values just to make it a little bit more clear where our focus is and where our directrix is. So I'm going to go ahead and say every mark is basically 0.25. And that'll make this a little easier to graph. All right, so my vertex is at 0, 1. And since the p-value is 4 and 1/4, and each of these lines now is 1/4, this is going to open up, so my focus will be here and my directrix will be here. And that makes it just a little bit easier to see. So directrix now is going to be y equals 1 minus 1/4, so 0.75. Focus is going to be same x coordinate, and then we add that to 1.25. Latus rectum for p is 1, so that means from the focus, I would go over a half, which on my grid is 2 lines. And then I have my parabola. All right, so last thing we're going to do is we're going to look at completing the square and inverses. So once I complete the square, then it's going to be the same exact question I just had. We're just going to do one extra step at the end to actually graph the inverse. So what I would do here is I'm going to start by rearranging. So I'm going to do y squared minus 4y plus blank plus 64 minus blank. And then I'm going to go ahead and move that 12x to the other side. So now what I'm going to do, in order to fill in that blank, take b, divide it by 2, and square it. So now that I have a perfect square here, so y minus 2 squared plus 60 is equal to 12x. And the last thing I have to do to get this as x equals is divide everything by 12. And I have my equation. So from here, vertex is going to be at 5, 2. P-value, so 1/4p is 1/12, so p-value is 3. Because p is positive and this is x equals and y squared, it's going to open right. So I'm going to move 3 to the right to get my focus, move 3 to the left to get my directrix. Latus rectum, 4 times p would be 12. Total distance is 12, so from the focus, I'm going to go up 6 and down 6. And the other thing this asked us to do was to find the inverse. So to remember, to find the inverse, we switch x and y. So to switch x and y, 5, 2 was my vertex, so 2, 5 will be the vertex of the inverse. Then 8, -4 was, so -4, 8 will be. Same thing, 8, 8 was, 8, 8 will still be on there. If I did the focus, that would become 2, 8. And the directrix, it was x equals 2. Well, now it'll be y equals 2. If I were to write the equation, switch x and y, and that should be the same equation that I just graphed. All right, so now let's do one last one. We'll go ahead and complete the square. I'm going to go ahead and move that 16y to the other side. The value that's going to go in the blank, 8 divided by 2 squared, that's 16. So x plus 4 squared minus 64 equals 16y. Divide by 16. And there's my equation. Oh, I lost my plus 4. And there's my equation. So then vertex, -4, -4. Sorry about that. It's going to open up. It's going to have a p-value of 4. So there's focus. There's directrix. Then I just need that latus rectum to get my last 2 points. That's going to be 4p, which is 16. So I'm going to go 8 and 8. And there's my parabola. So again, to find the vertex, I'm going to switch x and y. So there's my new directrix. -4, 4 is still -4, 4. But now instead of 4, 0, I'm plotting 0, 4 and 0, -12. My focus is now here. So there's my inverse. So you'll notice on this inverse that it is not a function. So this is something we're going to get into a lot more later this year when we look at square root graphs. Quadratics, in order for their inverse to be a function, we have to restrict the domain. And that's something we're going to do a lot of this year later on, but for now we're just kind of introducing that. So in order for this to actually be a function, let's say I restricted the domain of this quadratic to where it was just this part. Well, then the inverse would only be this part. And now the inverse is a function. So that's something we're going to do later on this year once we look at square root graphs. For now, if I want to write this just in terms of the same way we've written them for conics, it would just be x equals 1 over 16 y plus 4 squared minus 4. But again, that's not a function. So in order for it to actually be a function, we would have to restrict the domain of the original. Algebraically, the reason for that, let's say I just add 4 and multiply by 16. In order to actually solve for y, my next step would be to square root. Well, the problem when I square root it is it introduces both the positive and the negative square root. So the top part of this part right here, that's actually a positive square root graph. And then the bottom part of this graph would be a reflected negative square root graph. But again, we're going to talk about that more later on this year.